Hello everyone, my name is Greg. This is Chemistry News Selection channel. A couple of announcements. First, in the previous video about the Nobel Prize in Chemistry, I put links to a chemistry YouTube channel which describes in more detail the classical works of the Nobel laureates of this year. The channel name is Casual Chemistry, so please go to the description of the previous video. I also put them in the description to this video, and you can subscribe to his channel as well. Very cool stuff. Second, please subscribe to my channel if you didn't do it already. Also, this channel has a Telegram page, so subscribe to the Telegram. I make some announcements there once in a while. This video will feature several really cool things. Will include a lot of chemistry magic, but not this kind of magic, you know, when people make some volcanoes or put Mentos in the coal. It's gonna be more fundamental chemistry magic. It's something that you discover when you study completely not related things. And it also will include some, you can say, not current news, but rather future news. If anyone's interested and want to study the things I'll suggest here, do not hesitate to include me as a co-author. One more important announcement. 2 days ago, on December 19th, Professor Robert Grubbs passed away. So the next video is going to be dedicated to his memory. But the motivation for this video is some recent studies which are related to understanding of nature of some very unique chemical bonds. So first, a little bit about a chemical bond in general. Here you can see a general scheme of the energy of chemical bond formation, depending on a distance between the two molecules that react between themselves. It can be a hydrogen atom or it can be a bigger group, it doesn't matter. It all comes to the situation that two molecules are floating in the solution by themselves, then they come closer. Of course, not any two molecules will make this bond, but only those that actually attract to each other. Then those two molecules or atoms meet and a bond forms. This is a minimum energy. When the bond forms, electron basically mix, hybridization occurs. For example, if two hydrogens meet, then instead of two atomic orbitals, here it becomes a molecular orbital. And if you want to start pressing those atoms more, then you have an energy increase, because that's already not comfortable situation, unless you make an atomic fusion, which is already not chemistry but rather physics. In order to understand the chemical bond, it's interesting to see what happens in this region here. I mean, it's still not a fully bound molecule, but it's already not a free-floating atoms or molecules. And there probably are some local minimums here. It's not a smooth surface, probably, but it's very hard to detect the molecules in those regions. I mean, the orbitals in those regions, because it's very short-lived, obviously. People study it by femtosecond spectroscopy. People try to stretch bonds and study it this way. But today I'll tell you about a particular method of research of this topic, which can be called organic chemistry approach, and it is based on slowing down or interrupting this path from the free-floating molecules to the completely bound molecules by introducing large substituents on those molecules which do not let them to come closer. The first candidate of a molecule to study such interaction are radicals. You know, those molecules with unpaired electron, which have magnetic properties and which really want to make a bond between them. What radicals are known, which can be studied this way? First candidate probably is the first radical that was discovered in the beginning of the 20th century by Moses Gomberg, this 3-phenyl methyl radical, in which this carbon has only 3 bonds and the 4th bond is absent and it has an unpaired electron here. This radical is stabilized both by those bulky phenyl groups, but also by electron delocalization. So the electron is actually not present only on the central carbon, but can also delocalize to the rings, which has double bonds here. And interestingly, systematic study about how those radicals react one with another was done only in 2018 by a group of Peter Schreiner. It's actually an amazing work with a lot of synthesis and with a lot of compounds identification, very detailed. It focuses on the stability of radicals and on the stability of those dimers as a result of interactions between those R groups. And they check different R groups, starting from the smallest one, methyl, and ending with the biggest one, which is adamantyl. And they see how radicals become stable as a substituent here grows in size, but they also see how the dimer becomes stable when the interaction between the hydrogens on the R group grows. So it's a balance between Pauli repulsion, which is the hindrance between the bulky groups which repel each other, and London dispersion, which is type of Van-der-Waals interactions between the hydrogens. There was no chemistry beyond that was studied here. Another type of radicals that were studied are radicals in which the spin is localized on a central atom. And the first carbon radical of this type was discovered 100 years after the radical by Moses Gomberg, by Professor Apeloig and Dr. Dmitry Bava-Zhavatovsky. This radical was a byproduct. It was isolated in pretty low yield. It was a very important proof of concept nevertheless. The stabilization here was achieved by adding of silyl substituents, those bulky groups. With carbon, the problem is it's a little bit hard to introduce large bulky groups because the carbon atom itself is pretty small. Easier model perhaps is if we do a silyl radical with the spin localized on silicon, and it was done by Professor Sekiguchi for the first time in 2002. This huge radical with silicon in the center and with silyl groups, and it was isolated in already quite a nice yield of 44%. 7 years later we were able to show that it actually can be done in even higher yield. This radical, however, is completely not reactive. It's like a log. So what we did in our group later, prepared similar radicals with smaller substituents which allow the central silicon atom to interact. We generated radicals from disilyl mercury compounds. These compounds are light sensitive. When you irradiate them with visible or with UV light, the mercury atom falls out, two radicals form, and then in the solution they form the bond. Now those radicals you can see using EPR spectroscopy, electron paramagnetic resonance, and you can measure their decay, and you can measure their life in solution and see what happens with them. And we always observed second order decay. That means in every reaction event 2 molecules disappear. And we also measured the bond lengths of those dimers obtained from X-ray crystallography data and compared them to the stability of the radicals. We also compared the effect on the stability from the trimethyl silyl group versus the tertiary butyl group, and several other things. This molecule here was probably one of the most interesting ones because it featured a very long silicon-silicon bond, and in our paper we conclude that it's probably the longest possible silicon-silicon bond for molecules in which we have 3 silyl substitution on a central silicon. The problem with this is that in this particular case, unlike the others, this molecule was not isolated, it was calculated. So we could see radicals, we could see the decay, the second order decay, but when we check the products, we only see this silicon hydrogen compound, the silyl hydride, no dimer. And that's why it was not published in a good journal. It was published only as a conference book chapter, and we also couldn't really understand where this hydrogen comes from. We concluded that there might be some impurities in the solution which we cannot see, and despite Itzhak asked us a lot to check and to do some more experiments, we just wanted to rush forward with other publications and we just wanted to publish it somewhere and forget about it. So this mystery remained some idea could be that this hydrogen comes from the side groups, but there was no other silicon products, only pure hydride. It was also impossible, that what we thought, to come from hexane, because silicon radical is much more stable than the hexyl radical, so it's just thermodynamically impossible. But let's go back to this scheme of slowing down the interaction. Another idea was developed by Professor Stephan from University of Toronto, and he studied Lewis acids and Lewis bases. Lewis acid is a molecule that can accept a pair of electrons, and the Lewis base is the molecule that can donate a pair of electrons to a bond. And both of those molecules, if they're separate, they are completely stable, not like radicals, which are not very stable. But if you mix them together, they very, very quickly form this donor-acceptor bond, which is pretty strong. So Professor Stephan's idea was to increase the substituents size on base and acid and see what happens. Yeah, that's schematic representation of this idea. They cannot form the bond, but they really want to. And that's where the magic happened. If you mix those molecules together and check a spectroscopy of the mixture, you just see separate molecules. You don't see any interaction between them. But if you add a small molecule that can get into the space, like hydrogen or some small gas molecule, then reaction happens. Heterolytic reaction. So if you put hydrogen, for example, you get this phosphor hydrogen and boron hydrogen. So you got the hydrogen split. And if you, with any of those small molecules, some reaction happen. Of course, if you add those small molecules to separate base and separate acid, they do not react. Only if you add all of the three components together in one flask. And not only that, when you measure the kinetics of this reaction, it actually shows that the base and acid have some complex between them before reacting with the small molecule. This complex is called encounter complex, and it is purely theoretical. No one saw it so far. Take a minute to think about it. There is a complex that's present in a solution which you cannot see by any spectroscopy so far. I decided to make this video actually because it was just recently, a month ago, there was a review about this particular reaction. So each of those has pretty huge development. If you take only one of them with the dihydrogen, Professor Stephan just published a review about it. It just exploded since 2006. There is an interesting story to tell about this discovery. Professor Stephan wanted to publish it in JACS, but the editor of JACS then didn't like this idea. I mean, okay, so what happens? You just increase the size of the substituents, and why to call it a special name? And the special name here was, as you probably already saw, frustrated Lewis pairs. They are frustrated because they cannot form the bond. So he rejected the paper, but Doug didn't surrender, and he sent it to Science, and it was accepted. The editor of Science probably saw where it can go. I also wonder, can this sort of reactivity be found in nature? Maybe structural biologists should check if there's some active sites of an enzyme in which an acid and a base located in some proximity, maybe those acid and base do some interesting FLP type activation. But this is not the end of the story. Also in 2021, there was another review published. Apparently, you can take the frustrated Lewis pair and by irradiation or by some chemical impact, you can transfer an electron from Lewis base to Lewis acid and form a frustrated radical pair. So if you want, you can read the review. All the links are in the description below. I just want to show one particular reaction which I found pretty amazing, and here it is. So it comes from the reaction of this frustrated Lewis pair, phosphine as a Lewis base and aluminum triphenyl as Lewis acid. And when you add dinitrogen oxide to this mixture, this is intermediate that you form, the frustrated radical pair. And this frustrated radical pair can activate carbon-hydrogen bond, which is a very important reaction in organic chemistry. So this is what happens when the substituents on phosphorus are terch butyls. So it obstructs hydrogen from the terch butyl. But if you change those substituents to naphthyl substituents and add either toluene or bromobenzene, then the radical pair reacts with those molecules and not with the substituents. So with toluene you have a hydrogen abstraction from methyl, toluene is methylbenzene, and from bromobenzene you have even hydrogen abstraction from the benzene itself, while bromobenzene is not very good reactant for radical reactions. So this radical pair really do miracles here. And when I saw all those reactions with frustrated radical pairs, reminded me about one of our other publications which we did with stable radicals. And this is the paper we published. We prepared different stable radicals and studied their reactions. And this one of those radicals. It's actually pretty similar to the radical I showed before, this one from Professor Sekiguchi, but it has a bigger tail here with a silicon hydrogen bond. And this radical is yellow. When you solve it in hexane, it's yellow. I actually just simply left this tube on the table with the radical solution and went home. Next morning there was sun. And when I came in the morning, I see that the tube, instead of being yellow, became blue. And when we studied what happens there, we saw that under irradiation, one radical obstructs hydrogen from another radical. This double bond forms, and this molecule is blue. It was known before. And the second product is this compound with the obstructed hydrogen. And we suggested the following mechanism of this reaction. This mechanism was supported by quantum mechanical calculations to some extent, was well received by the reviewers of the publication. And the suggested mechanism is an electron transfer from one radical to another as a result of irradiation, with formation of this anion and this cation, and then some proton transfer. But look at this reaction closer. We have two radicals which are too big to attach to each other. And after transfer of an electron under irradiation, we have plus and minus, which is Lewis base and Lewis acid. So it's frustrated Lewis pair. Can we see this reaction this way? Back then, we didn't know about this chemistry. It was just very young and we missed this publication in Science from Professor Stephan. But when I'm looking back, it now makes more sense. This was not the only finding in this paper. We also studied the reaction of this radical. And because we thought that this reaction is basically a hydrogen abstraction, so we tried to make similar reaction under irradiation with this radical, and we put known hydrogen donors like 3-ethylsilane or isopropyl alcohol, and we saw that actually this reaction happens under irradiation. Indeed, without irradiation or without adding those hydrogen donors, this radical is stable as a log. But what we didn't think that maybe what we have here, that this reaction happens, that one radical gives electron to another radical, exactly like before. And actually maybe those molecules are those that react with the 3-ethylsilane or isopropyl alcohol, because there were also other products which we didn't identify. And if that's the case, we have a photo-induced frustrated Lewis pairs. This one would be new, and it's very, very interesting to see how it reacts with small molecules, like the frustrated Lewis pairs react with the hydrogen, or maybe with the polar molecules like the nitrogen oxide, and so on and so forth. And okay, we spoke already a little bit about the frustrated Lewis pairs, but what is its mechanism, how it works? We saw the mystery. Is there any answers to the mystery? And in 2017 there was a pretty cool paper from this group from Belgium, in which they actually studied the mechanism by quantum mechanical calculations, and they reviewed two theories about what can happen there in the middle of the Lewis base and Lewis acid pair. So one idea was that when the small molecule comes between them, there is an electron transfer which wants to go from base to the acid, and hydrogen here is like a bridge for this electron. And there was another model, which they call electric field model, is that because there's partial positive charge and here's negative charge, there is electric field emerges between boron and phosphorus, and when the small molecule like the dihydrogen comes between those atoms, it polarized, and as a result of the polarization, the electrons start to flow from hydrogen to the acid. And then when the electron flow here, the base become active and that obstructs the remaining hydrogen here. And they were able, by those quantum mechanical calculations, to show pretty nicely that this mechanism prevails in the frustrated Lewis pairs. While this mechanism probably unlikely because the activation energy for the electron coming from the base to the sigma star of the hydrogen is very high, is about 30 kilocalories per mole. I didn't see studies about frustrated radical pairs, and correct me if I'm wrong. I hope it will come soon from this or another group. But if you compare the energy, the bond formation between phosphorus and boron is about 30 kilocalories per mole. But the energy of coupling between those two radicals, the silyl radicals which we discussed, is around 60 kilocalories per mole. It's twice higher. So that means that the potential of this reaction between the frustrated Lewis radicals is probably much higher. It may activate much more reactive bonds, and we saw the carbon-hydrogen bond activation before. However, there it's hard to say was it simultaneous activation by both radicals or not. I have an idea of a possible simultaneous activation, and it comes from the reaction I already showed in this lecture. So one possibility is that this hydrogen could come from the solvent. Why we discarded it? Because if silicon radical obstructs hydrogen from hexane, you will get a hexyl radical, which is much less stable. So it's just impossible thermodynamically. But if we don't look at this as a hydrogen obstruction, but as a reaction of frustrated radical pair, what do I mean by that? So we have a mercury here that goes out under radiation and we get those two radicals. Those radicals are actually smaller than the one from Professor Sekiguchi. It has less bulky substituents, but still bulky enough to prevent the dimerization, and that's why we don't see the dimer. But we have also this space here, which is probably enough for entrance of hexane molecule. And maybe both radicals work simultaneously and obstruct two hydrogens simultaneously. And this is how the second order decay explained. This cannot be explained by dimer formation, because dimer, if it forms and then decomposes back, we would not see a decay, but we see a decay. At second order decay, without light. So the product here would be in the molecule with carbon-carbon double bond. And if you do the thermodynamic calculation of two radicals and hexane versus two silicon hydrogen compounds and hexene, then the picture will be completely different. So this reaction is thermodynamically favored. So what we need to calculate now is the transition state to see is this the mechanism possible. And if this is the case, then it's not just simple carbon-hydrogen bond activation. This is hydrocarbon cracking. That's the first stage of crude oil rework to produce polymers, to produce pharmaceuticals, and so on. Now, this process is done by very, very expensive and high temperature processes. So if you can do it at room temperature and without precious metals, you can consider publishing in Science. I'll tell you even more. When I checked this reaction mixture, I saw double bonds, carbon-carbon double bonds, but I thought it's impurities. I couldn't believe that this radical can obstruct hydrogen from hexane. So all you need to do is to make it attractive to industry. Probably use something else instead of mercury, maybe zinc. But of course, first we need to prove that this reaction happens with hexane and with other hydrocarbons. So this is it. Have a good day.